好，我们继续哈。这边开始的话是一个 general 的 expression 了哈。那我们只是把两个的相位差，本来是 phi x 跟 phi y 的哈，替代成 delta 加 phi x， 因为我们把 phi y 定义为 把 delta 定义为 phi y 减 phi x 嘛哈。Because we define phi y delta as phi y minus phi x, so we substitute phi y with delta plus phi x. So let's assume phi x equal to 0 because you have phi x in both terms. So it's you are just taking an offset. So your x component goes with cosine omega t, and your y component goes with cosine omega t plus delta. And the instantaneous ratio of EY over EY sub 0 becomes a function of cosine omega t plus delta. And it can be decomposed into cosine omega t, cosine delta, minus sine omega t, sine delta. So if we do the same thing for EX component, EX over EX sub 0 component is cosine omega t, then we can substitute cosine omega t with EX over EX sub 0 over here. So you end up with this. And this equation, if you're looking carefully, if you move the first term on the right-hand side of the equal mark to the left, then taking the square on both sides, you end up with this equation. And if you rearrange the things of this equation a little bit, you end up with this equation. And this is equation for the locus of an tilted ellipse, 倾斜的椭圆形的函数啊，倾斜的椭圆形函数。为什么说它是倾斜的 ？Why we say that it's a tilted ellipse? If you set delta to 90 degree, positive or negative 90 degree, then this term goes to 0. Then you have ES component to the square plus EY component to the square equal to sine delta to the square, equal to something. If cosine delta equals to 0, that is delta equals to odd multiples of half pi, then you end up with these things, and this is the so-called fixed ellipse. The ES component and EY component does not necessarily to be the same. One can be greater than the other. The larger one is referred as the major axis, and the smaller one is referred as the minor axis. Then you have an ellipse that is located on the x-axis or y-axis like this. So if you have same size for your major and minor axis, I mean the first term and second term are the same, you end up with a circle. Then you will have the so-called right-hand circular polarization or left-hand circular polarization. So the definition of axial ratio, which you came across quite often for antenna design, is defined as the major axis over minor axis ratio. Okay? But usually we are looking into the absolute value of axial ratio. And here, with this definition, you know, axial ratio can be a positive number or a negative number from 1 to infinity and minus 1 to infinity. If it is a positive number, it stands for left-hand circular polarization. If it is a negative number, it stands for right-hand circular polarization. But usually, when it comes to antenna design, we usually take in the absolute value of the axial ratio. So we know that an antenna with good circular polarization property, you usually require the axial ratio to be smaller than 2 or 3 dB, right? 2 is the same as 3 dB. So which means for circularly polarized antenna, the axial ratio should be smaller than 3 dB, or its absolute value should be smaller than 2. If the axial ratio is too large, which means the major axis is much larger than the minor axis, then it approaches to what? To linear polarization. For linear polarization, you have only the major axis turn and 0 minor axis turn. So for linear polarization, the axial ratio is infinity. Here is another interesting thing about right-hand circular polarization and left-hand circular polarization. If we use X and Y, a vertical two linear polarization and their composition, the addition of X and Y component with proper phase delay can be used to synthesize right-hand circular polarization and left-hand circular polarization. So on the very top, you see the unit vector for left-hand circular polarization can be defined as 1 over square root of 2 times X plus JY. X hat and Y hat are unit vector on the X and Y direction. And right-hand circular polarization can be defined this way. Here the EY phase is lag behind the EX term. So you can write up unit vector for RCP and LCP in terms of combination of EX component and UI component. The result abides property like this. The dot product of ELCP, the unit vector, LCP unit vector itself, and its complex conjugate equals to 1. The dot product of RCP unit vector and conjugates of the unit vector equals to 1 as well. The dot product of LCP unit vector and RCP unit vector is 0. Why? They are orthogonal to each other. Just like vertical polarization and horizontal polarization are orthogonal to each other, right-hand circular polarization and left-hand circular polarization are orthogonal to each other too. So here is another way to decompose the radiation composition. 也就是说，你可以用垂直极化跟水平极化去分解、拆解一个任意方向的电磁波、电磁场。你也可以用左手成分跟右手成分去拆解任意的电磁场。So you can write up an arbitrary polarization in terms of LCP term and the RCP term. Okay. And here are some interesting results. So if you use, so the implication of the result in the previous slide tells you that if you try to receive right-hand circularly polarized wave with a left-hand circularly polarized antenna, how much energy can you have? None, right? Nothing. Because the two polarizations are orthogonal. So if you try to use left-hand circularly polarized antenna to receive linear polarization, how much can you receive? Half. Only half of that. Because left-hand and right-hand circular polarization are composition of two linear polarization, right? So you try to perform dot product of the left-hand circularly polarized unit vector and right-hand circularly polarized unit vector with an arbitrary E field. And you see the two are become orthogonal to each other. So, anyone have tried to design circular polarization antenna? 有没有人做过原极化天线的设计？应该有了哈。只要你有做过原极化天线的设计，你要如何证明你的天线是有原极化的辐射场型 ？How to verify that you have designed a circularly polarized antenna, or you have to validate that you design an antenna with right-hand circular polarization. In HFS, you draw the radiation pattern, right? This is your RCP pattern. Is this enough? This is not enough. You need to draw the LCP pattern at the same time. Okay, if the LCP pattern looks like this, do you have left RCP? Do you have a circular polarized antenna? No. If the magnitude of RCP pattern and LCP pattern are about the same, you are actually design a linearly polarized antenna. Okay, so usually, if you successfully design a circularly polarized antenna, if you draw the RCP pattern and LCP pattern at the same time, you may end up something like this. Your RCP pattern difference must be large so that you can ensure that radiation toward this direction are mostly RCP. Okay, are mostly RCP. Okay. 所以，假如你要验证的话，你通常是要同时画出来 ，LCP 跟 RCP 同时画出来。All right. Here, in this part of lecture, let's try introduce another description for polarization. This is the so-called Poincare sphere. Poincare sphere, okay, invented by Poincare, right? Of course. We already introduced the circular polarization representation using gamma and delta, and here are the definition of gamma and delta. The Poincare sphere uses parameter epsilon and tau to describe the states of polarization of the wave. Use gamma, epsilon and tau. So what we need to know is the definition for epsilon and tau. So let's look at the definition. Epsilon is the arccotangent of the actual ratio. In other words, the X ratio is the cotangent of epsilon. Epsilon here is the arccotangent of the actual ratio. Tau is the slant, the tilt angle. And tau can be in the range between 0 to 180 degrees. Is actually the angle between the major axis and the EX. So for this ellipse, the major axis is pointing this way. The angle between major axis and the EX is tau angle. And epsilon is between minus 45 degree to 45 degree. Poincare sphere. So let's take a look at the Poincare sphere first. You use epsilon as theta for your sphere. Now, if you have a sphere, the epsilon is kind of the theta angle. We know that theta angle is between 0 to 180 degrees. But for point carré sphere, for point carré sphere, theta equal to 0 equal to 45 degree, 180 degree. Now, down below is minus 45 degree in terms of epsilon. The other angle tau is for phi. Tau is between 0 to 180 degree, and it's complied with 1 to 360 degree as phi. Okay? And for anything on the equator, that is epsilon equal to 0. If epsilon equal to 0, it's a linear polarization. If it's in the northern hemisphere, on the top of the sphere, it's a left-hand circular polarization. Left-hand polarization. If its location is in the southern hemisphere, then it's a right-hand polarization. Okay, so everything on the equator is a linear polarization. On the very top of the z-axis is left-hand circular polarization, which equals h as epsilon equals to 45 degree. On the opposite, at the minus z-axis direction, you have a right-hand circular polarization. Okay? So here is the expansion of the Poincare sphere. As you can see here, from tau equal to 0 to 180 degree, you have a horizontal linear polarization, vertical linear polarization, and horizontal polarization again. On the top are left-hand polarization, and on the bottom are right-hand circular polarization. So the things that you need to be aware is the transformation between gamma and tau to epsilon, gamma and delta to epsilon and tau. See example 4.9, 4.10, and 4.11 in your textbook. Yeah, you will come across one of the problem in your midterm for this. Okay. So once you substitute it, and this equation will be provided on the exam sheet. 所以不用去背它了，只要用到的话，我会放在题目里头，可以吗？我其实不喜欢要求人家背式子了，因为式子其实就在课本里只是我也不喜欢开书考了，我在美国的时候最怕就是开书考，开书考就算了，还让你带回家考，还让你带回家1个礼拜，那种最痛苦的。那种是最痛苦的。我宁可在课堂上花2个钟头把它考完，那个反而比较轻松，比较好准备。好，所以相关的题目要回去要记得练习哦。考古题也有这个题目哦，考古题也有这种题目这种转换，好不好？ So let's take a look at a few examples. So here we have an electrical field representation of phi x at x minus 10 at y, which is exponential minus j beta z. So we know the two are 180 degree out of phase, 180 degree out of phase. So delta is 180 degree. The tilted angle gamma because EX component and EY component is 1 is 2, the other is 1. So you can calculate the angle between the two. The angle can be taken as the arctangent of 10 over 5. So it's 63 degrees. We know that gamma is between 0 to 90 degrees. So we want to find out what epsilon and tau are on the Poincare sphere. So we substitute delta and gamma value into the transform equation. So here we use sine of 2 times epsilon equals to sine of 2 times gamma times sine of delta. And because sine of delta equal to 0, everything equal to 0, so epsilon equal to 0, which means it stays on the equator. It must be a linear polarization. The tau value of the wave of the field can be found as tangent of 2 gamma times cosine delta. Cosine delta equals to -1 because delta is 180 degrees. So you have tau equals to 233 degrees. 2 times tau equals 233 degrees, so tau equals to 116 degrees. So it's drawn on here. It's a tilted linear polarization. Tilted linear polarization. This is 90 degrees, this is 180 degrees, this is 135 degrees. So 116 degrees is here. And the other example, here's another example. No, here's the same example. Here we also try to express the E field in terms of right-hand component and the left-hand component. So what we do is times the E field with complex conjugate of LCP unit vector and the RCP unit vector to get the LCP component and RCP component. As you can see here, the magnitude of the two components are the same. So you have the same magnitude for right RCP component and LCP component. What is the implication of that? It's linear polarized. Okay? Because the RCP component and the LCP components are about the same weighting. Here is another example. X component is J5, Y component is -10. So X component is 90 degrees, Y component is 180 degrees. So delta, the difference in phase is 90 degrees. And it's greater than 0. So we know it's a left-hand polarization. Gamma is 63 degrees as the previous case. So it's elliptical because this is not 0 or not 90 degrees, so it's elliptical polarization. And you can find the epsilon and tau value from delta and gamma. You end up with epsilon equal to 26 degrees. We know it's on the upper hemisphere, northern hemisphere. So it's left-hand polarized. Tau is 90 degrees. Tau is 90 degrees. So it's aligned. Its major axis aligned with the y direction. So it actually is drawn in this red ellipse. And if you try to represent it with right-hand circular polarization component and left-hand circular polarization component by taking the dot product of the RCP head and LCP head, you can find out the component. Okay, so you see the magnitude of A is greater than B. So its component is, the left-hand polarized component is heavier than the right-hand one. All right? Okay, that's about it